Hi everyone. So we have been looking at continuous uniform distribution in a couple of our previous sessions where we looked at how we can calculate different metrics for a uniform distribution, including how we got the PDF, which was the height of the probability density curve. We use the property that area of the region has to be 1 because area under the probability density curve represents the probability of x to lie in a particular range. Therefore, if we add up all the area in the given x range, the total area should be 1 since the sum of all probabilities should be 1. So using that, we got the probability density function as 1 upon b minus a for a uniform distribution. Then we looked at a cumulative distribution function, which is a function which gives the probability of the random variable taking a value less than equal to x, and it was obtained as x minus a upon p minus a in the given x range. Next, we looked at how we can get the mean and variance for uniform distribution. So we used an analogy from our discrete distribution case where we were having the mean computed as the summation of the values of x with their corresponding probabilities or corresponding probability mass function values. Here we integrate the same product of x with the probability density function, and we integrate it in the required x range, which is the total x range, to compute the expected value, and we obtain that value as a plus b upon 2 for the uniform distribution. Then for variance, we calculated the variance as the difference between the second movement of x with the square of the mean, and once again we use the same integral method to get the second movement of x, and we obtain the value as b minus a whole square upon 12. Then in the very previous session, we looked at how we can get the percentile values for any distribution. Pth percentile value means that there are p percentage of the total values which are less than equal to that pth percentile value. This can also be worded as the probability of getting a value which is less than equal to the pth percentile value is equal to p. We use the cumulative distribution function to get the required pth percentile value. Using the same function, we were able to get the median, since median is nothing but the 50th percentile value. Therefore, we simply equate the CDF value equal to 0.5 to get the required median value. And we saw, since this is a uniform distribution, the median value would be nothing but the middle value of the total range, which was a plus b upon 2. Next, we looked at how we can get the first quartile, third quartile of a distribution. So first quartile was the 25th percentile value, while the third quartile was the 75th percentile value. Using the difference between the two values, we got the interquartile range for the given distribution. Finally, we also looked at the relationship between the PDF and CDF of the function, where we looked at how PDF could be obtained as the different derivative of the CDF of the same function. So we differentiated and we got the required PDF back from the CDF of the function. So this is all which we have been looking at. Now to jump to the next distribution, next continuous distribution, which would be an exponential distribution, we wanted to first go through some of the basics of differential calculus, because in the future distributions, continuous distributions, which we would be looking at, we might want to we'll be using some concepts from differential calculus, and therefore it becomes an important topic. And also in general, it will be used in a lot of things while we are studying different methods in optimization in machine learning, like gradient descent and other optimization methods which use differentiation a lot, and therefore one should be aware of at least the basics of what differentiation means and how we can compute the derivative of different kinds of functions. So first we'll try to define from basics what differentiation means. So let us say we have a probability density curve, as you can see on the right side here. So this is a probability density curve in a given x range. So this is the total x range here. Now let us say we want to calculate the derivative of this function at this particular point. Now derivative of the function is nothing but it is the instantaneous rate of change of that function at the given point. Now let us say in this particular small part of the function, we are magnifying it here, and let us say we take a very small part here, and we see that the function moves from this particular point to this particular point. And since this is a very small part which we are taking, let this small part be given as delta x, and this particular x value is x, and therefore this value would be x plus delta x. Now we already know the function, so if this is x plus delta x, we know the value of the function at x plus delta s as f of x plus delta x, and therefore this would be f of x. Now once we have done that, how do we define the rate of change? Rate of change would be nothing but change divided by the total distance traveled. So the rate of change is nothing but the total change that has happened while we are going from the left to the right side, that is we are traveling a distance of delta x. So in this case it would mean f of x plus delta x minus f of x divided by delta x. So this is the change in function value, and this is the distance traveled for that change. So we are dividing the total change in the function value with the total x value that we have moved to get the required change. Now one thing to point here is we are looking at an instantaneous rate of change. Now for instantaneous rate of change, we would need delta x to be a very small value, and therefore it has to tend to almost a zero value, since we are looking at a point here instead of having a range. So we can convert. So since we are calculating the derivative, we can write it as dfx upon dx, and this can be written as limit delta x tending to 0 f of x plus delta x minus fx upon delta x. So this is how we compute the derivative of any function, any probability density function or any function in general, and this is also called the limit definition of derivative. So we'll just write it here. This is the limit definition of the derivative. So this is how we get the derivative of function, and if you note here, this value is also nothing but the slope of the function at that point. This can be actually seen from this magnified image which we saw earlier. We can see that if we form a triangle here, so this particular image, if we form a triangle here, we are actually calculating this particular value, tan of this particular value, which is the slope, because tan theta is defined as h upon b, that is height upon base, and the height is nothing but the change in the function value, and the base is nothing but the total distance traveled, that is delta x. So this is actually the base and this is the height. So therefore this is the derivative of a function, can also be said as the slope of the function at that particular point. So we always compute the derivative at a particular point as seen in this case. Now there are some basic rules of differentiation which you can actually get it from anywhere, but I'll be just going through some of the basic rules here which would be used in the different applications we'll be looking in our future sessions. So the first one, the basic rule: the derivative of a constant is 0. Now I think this can be intuitively understood as well. Since it's a constant, we are looking at a constant horizontal curve here, and tan of 0 is 0. Therefore the slope would be 0 at every point, and therefore a constant has a derivative of 0. Next, we will be looking at a power rule. So now we'll be looking at some of the rules which can be applied directly. You don't need to understand how we arrived to those rules, but we'll be looking at some examples as well. So a is a constant here, so this is a constant. So whenever you find a constant, you can straight away bring it out of the derivative operator and operate on the remaining part. So a is brought outside here, and we are left with derivative of x to the power n divided with respect to x. So this is a multiplied by n plus 1. Oh, it's x raised to power n minus 1. So we simply subtract the power by 1 to get the required derivative, but we also need to put in n here. So the derivative of x raised to power n is nothing but nx raised to power n minus 1. So this can be actually remembered, and this is a very basic rule again in differentiation, and therefore this can be easily remembered. So for example, we need to calculate the derivative of x cube. It would be 3x square. So we are using this becomes n and this becomes n minus 1. So this is the power rule of differentiation. We can have some more complex examples here. So for example, if we need to find the derivative of root x. Now root x is nothing but this is actually equal to x raised to power 0.5. Therefore, the answer would be 0.5 minus 1, which becomes 0.5 minus 0.5. This is 0.5 divided by root x. So this is the required derivative for square root of x. So basically the power could be anything. So n could be fractional or decimal or even negative value, and still we'll get the same derivative formula. So we can still use the same derivative formula. So another example could be, let's say we want to calculate the derivative of, let's say 5 into x raised to power 0.15. So once again we bring 5 out, and the derivative of x raised to power 0.15 would be 0.15 multiplied by x raised to power minus 0.85, because 0.15 minus 1 is minus 0.85, and therefore this could be written as 0.75 divided by x raised to power 0.85. So this is how we can get the derivative of any function with the power. So this is it regarding the power rule. Next, we want to understand derivative of linear functions. So let us say we want to calculate the derivative of 3x4 plus 2x cube minus 5x plus 6. Now there are 4 terms here, and we are either adding or subtracting them. So we can actually find the derivative of them. So find derivative separately and then use the same operator like addition or subtraction to finally add the answer or subtract the answer. So the derivative of 3x raised to power 4 would be 4x raised to power 3 plus 3x raised to power 2 minus 5. So derivative of x is 1, therefore we'll be left with minus 5 only, and derivative of 6 is 0, so this is 0. This becomes 12x cube minus 6x square minus 5. So this is again a very basic rule of finding the derivatives of functions which are linear combinations of different terms in x. So this is regarding the linear functions derivative. Next, we'll be looking at the product rule of differentiation. So again, this is a very important rule. So let us say we have to compute the derivative of a function of x, which is ux, and so in this case there is no linear operator between ux and vx, but we are multiplying the two functions in x. So what happens here is, so another thing to note, d of f x upon dx has another notation which is called f dash x. So the dash here, this particular value, this particular notation means first derivative. Similarly, we can have the second derivative as two lines here, two small lines here to denote the second derivative, and this can be written as this particular function. So this is how we write the second derivative. By second derivative, we simply mean we are differentiating the same function twice. So for example, if we have to find the second derivative of 5x square, what we do is we first differentiate it once. So 5 into 2, 10 and x, and we simply differentiate it again, which is equal to 10 here. So this will be the second derivative of 5x square, and this is represented by f double dash x. Now the product rule states if we have a product of two functions both in x, the derivative is computed as du of x upon dx multiplied by vx plus dv of x upon dx multiplied by ux. So in short, it could be written as u dash x vx plus v dash x ux. So this is how we calculate the derivative of two functions which are in a product form. So for example, now let us take an example of fx x square minus 5 multiplied by 6x plus 2. Now let us say we need to find the derivative of this particular function. So df upon dx we need to find here. So what we do, we take this as ux and we take this particular function as vx. Now u dash x, or the derivative of u with respect to x, is 2x, since the derivative of x square is 2x and derivative of minus 5 is 0, since it's a constant, therefore we'll be left with 2x. And the derivative of v dash x, or derivative of vx, is v dash x, which is given as 6, since the derivative of 6x is 6 and for 2 it will be 0. Now we can find f dash x as u dash x vx plus v dash x ux. This can be written as 2x 6x plus 2 plus 6 x square minus 5, 12x square plus 4x plus 6x square minus 30, and therefore we are left with 18x square plus 4x minus 30 as the required derivative of the function f. So this is how we can use the product rule to calculate the derivative of two functions which are in product to each other. So this was regarding the product rule of differentiation. Next we move to quotient rule. So just like product, we can also have the ratio of two functions. So let us say we need to find the derivative of fx upon gx. So what we do, we simply square the denominator and keep it that as it is, and in numerator we again take gx f dash x, and this time there is a minus fx g dash x. So this is how once again one can remember actually this formula, because it would be used again and again in many of our applications, both in machine learning and deep learning. So this is regarding how we can use the quotient rule to get the derivative of the ratio of two functions. Now let us say we have to calculate the derivative of the ratio of 5x minus 3 with 2x plus 1. So we simply square the denominator like we saw. We write it as it is again, and the derivative of numerator is 5. We subtract, we write the numerator as it is, and derivative of denominator is 2. So this is 2x into 5, 10x plus 5 minus 10x, and then minus minus becomes plus 6 upon 2x plus 1 whole square, and therefore we are left with 11 upon 2x plus 1 whole square. So this is how we can use the quotient rule to get the derivative of any ratio of two functions in x. So this is how we can calculate for products, and for ratios of functions we use these two rules to get the required derivative. Now moving further, we will be looking at something called the chain rule or substitution rule. Now this is very important because this will be used in our next few sessions as well. So what we are looking at here is, it is possible that we get a case where we have a very complex function, and that particular function could be written as a function of another function. So for example, f of gx. So an example of this first, let us say what does f of gx means. So let us say we have a function called e1 minus e to the power minus 5x. Let us say this is a function. Now let us say, since it is also called the substitution rule, let us try to use substitution here. So let us say we put u as 5x. Now this was fx, and let us say we are giving u as 5x. So again, u could be, this could be written as gx as equal to 5x, where gx is another function of x itself. Now fx could be written as 1 minus e of minus gx. So now we see that fx itself has become a function of gx here. So instead of finding the derivative of fx, we are actually finding the derivative of f gx, which are exactly the same things. So how we do that? The derivative of f of gx is computed as, using the chain rule, as f gx g dash x. Now we can write it in a more clear way as d of fx with respect to d of gx. So instead of differentiating it with respect to x, we are first differentiating it with respect to gx itself, because it would be easier for us to do so, and then we are differentiating gx with respect to x. So this particular term here, g dash x, is this term, and f dash gx is this term. This is how we get to we use the chain rule or the substitution rule to get the required derivative. Now a very simple example of this which we'll be using here could be, let us say we have to find the derivative of fx x square plus 2x plus 3 whole square. Now let us say we define gx as x square plus 2x plus 3. Then we know fx could be written as gx whole square. Now f dash gx, which is dfx upon dgx. So we are differentiating fx with respect to gx, would be nothing but 2 of gx. This is because gx can itself be considered as a variable, let's say y, and the derivative of y square is 2y. Therefore we have 2 of gx as the derivative here. Next, for the second term of the chain rule, we need to calculate the g dash x as well. So g dash x is 2x plus 2, because the derivative of x square is 2x, and the derivative of 2x is 2, and the derivative of 3 is 0. So we can ignore that and we get this particular value. Now remember that this 2gx is still 2x square plus 2x plus 3. Therefore f dash x, which is f dash g of x, g dash x, can now be written as 2x square plus 2x plus 3, 2x plus 2. So we bring the 2 out from here, we are left with 4 here, and x square plus 2x plus 3 multiplied by x plus 1, this can be written as x cube. So plus 1 x square and plus 2x square is 3x square, and plus 2x plus 3x would be plus 5x plus 3. So this would be the required derivative of the given function. We can actually leave at it at this as well. That would be enough. And this is how we can use the chain rule to get these various derivatives. Now one thing to note here, let us say we had this particular function which we saw earlier in an example. Let us say we had f of x 1 minus e to the power minus 5x. Now instead of taking gx as 5x, we could have also taken gx as minus 5x, and in both ways we would have been able to calculate the required result. So now let us say we take it as minus 5x in this case. So we have f of x 1 minus e to the power gx, since gx is minus 5x. Now another property or basic rule for derivative is that the derivative of e to the power y with respect to y is e to the power y itself. So for e to the power y, the derivative is same as the function itself, and therefore if we calculate f dash g of x, we would be getting, so the derivative of 1 is 0 and the derivative of e to the power gx is e to the power gx, therefore we are left with minus e to the power gx. And next, the derivative of minus 5x is minus 5, since the derivative of x is 1 and we can bring the constant minus 5 outside. Now we simply put both the values here to get f dash x as f dash gx g dash x, which is 5 e to the power gx, which is minus 5. So this is how we can get the derivative of any function of functions here. So f of gx is nothing but a function of function. It can actually be written as f of as well. So by f of f, normally f of f is written as a function of fx itself, which means f of fx. But basically f of gx, you can call it as f of gx as fog as the given function, or you can write it as fogx. This is another way to write the function of another function. Okay, so now that we have learned the basic rules, so once again we looked at the three basic rules were product rule, then we had quotient rule, and then we had chain rule. So the product rule was the derivative of uv with respect to x is u dash v plus v dash u. The derivative of u upon v with respect to x, so this is product, this is quotient rule, it was we put v square, write v as it is, u dash minus u v dash, and then d of f of gx with respect to dx is f dash gx with g dash x. So these are the three major principles, you can say, which we would be using to find the derivatives of complex functions in general. Now there are some very basic rules which actually we started with. So if you remember, we know that the derivative of constant was 0. Then we looked at the derivative in terms of power law, and this was given as nx n minus 1. Then we also looked at e to the power x. So this was same as e to the power x. Then we can also calculate the derivative of ln x, that is log of x. This is nothing but 1 upon x. Then for trigonometric ratios, sometimes it becomes important in some of the NLP problems. We'll actually using these. So t of sine of x is cos x, d of cos x is minus sine x. And next, let us try to derive the derivative of d of tan x instead of remembering it. So tan x is nothing but sin x upon cos x. Now if you remember, this is actually an application of a quotient rule here, since there are two functions in a ratio form here. So if you remember, the derivative is nothing but we square the denominator, we write it as it is here, u dash minus u v dash, and therefore we get the derivative as cos x. The derivative of sin x is cos x minus sin x, and the derivative of cos x is minus sin x. So this is cos square x plus sin square x upon cos square x. Cos square plus x plus sin square x is 1. Therefore 1 upon cos square x, which is nothing but sec square x. So the derivative of tan x is nothing but sec square x. So this is how we can actually get derivatives of many complex functions. And now that we have some understanding of finding the derivatives of exponential functions and trigonometric ratios, as well as the log function. So the log function, it was 1 by x, and I think we are good in terms of finding the derivative of most of the functions. So just using these three rules basically, product rule, quotient rule, chain rule, and then some of the basic rules like the constant, power law, exponential, log, and trigonometric ratios, we should be able to calculate the derivative of almost all the functions which would be used in applications of machine learning and deep learning in general. So this is it from this particular session. In the next one, we might be looking at some of the applications for derivatives, what we have seen in this session.